I'm going to talk a little bit about the USC Foundation, especially about the USC approval program, because we are talking about repair parts and lead-free issues. One of the big issues is lead-free repair parts and lead-free assemblies that get repair parts that are or are not lead-free, and does the assembly maintain its approval or not? And so that's what's going to be talked about. So I will spend a little bit of time talking about the approval program, just so you have a basic understanding of that before we get into all the details of the repair parts and lead-free issues. We will have a webinar that is exclusively devoted to the USC approval program on February 7th. That'll be a 3-hour webinar, and that'll give you a lot more details about the USC approval program. But I will discuss a little bit this morning so you get a general idea of the USC approval program, how it works. But first of all, I'm going to talk a little bit about some of the history of the USC Foundation. We'll talk about the standards for backflow preventers, how they were developed, how they continue to be developed, the approval program, and then the status of an assembly being approved and maintained in its approval, membership program, training program, and a little bit of research. So let's talk a little bit about the history of the USC Foundation. Back in 1880 is when USC was founded, so a long time ago, 145 years ago, USC Foundation, the university was founded. And you can see from the picture here back, we were way on the outskirts of Los Angeles. This was the entire university, this one building, which is still on campus today. About 65, 64 years later, the USC Foundation was founded. And what happened was there was an incident in the Los Angeles harbor where a supply ship was leaving the harbor. This was during the Second World War, and before they got very far, people started getting sick. And it was determined that the freshwater supply on board had been contaminated with harbor water. They looked into it, and it was traced back to a cross connection on the dock where the harbor water was cross connected with the freshwater lines that were lining the docks. Because of this incident, some people got together and decided this was something that needs to be looked into, and they came to the university. This was an anonymous group of men came to the university and gave the university some money and said, we would like to have USC look into this, do some research on this, what can be done to prevent this sort of thing from happening. So then in 1944, after that, the USC Foundation was established. Why did they choose USC? A couple reasons. Obviously, USC has been for a long time a major research institution, one of the top research universities in the world. And obviously, we're an educational institution. We're not biased in the sense that we wouldn't be like an organization or we wouldn't be a manufacturer of backflow preventers, so we're trying to promote our own product or anything where we would have financial gain from that. So it's an unbiased institution. It's private. So we're separated from government institutions and stuff. So these are some of the reasons they went to USC and decided to have USC look into this issue. So they gave the university some money. Universities established the foundation, and the foundation started to look into this problem of cross connections. Eventually coming to the point where they would develop standards. But the first thing we did was we looked into some of the valves that were out in the field, because some valves had been installed in the field because there were some cross-connection incidents that had occurred. In the early 30s, there was a big incident that occurred here in Los Angeles, and the Department of Water and Power had put in some valves, some check valves, basically to prevent that sort of thing from happening again. And there were several of these valves installed around the city, so we went out and started looking at them and determining, were they still working, were they doing any good, and we found out that I actually believe all of them were not working anymore. So it was determined that the single check valve, the valves that were used at that point in time or that had been installed, were not working any longer, were not doing what they had hoped that they would be doing. So the USC Foundation worked on developing standards for backflow preventers. The first standard was published under a paper called paper number 5. I mean, it was the 5th paper published by the School of Engineering. It was then the USC Engineering Center. The 5th paper published that year, and they were the first standards for backflow preventers by over 2 decades. No one else developed standards for backflow preventers for another 20 years. But the first standards for backflow preventers published in paper number 5, fairly basic. Those were updated and developed. Again, there was a paper called USC EC 48101, which was published in 1959, and then after that we came to the that's paper number 5. Then we came to the first edition of the manual in 1960. Looking at the original standards, back in paper number 5, we have laboratory evaluation, and then there was a 6-month field evaluation. After the 6-month field evaluation, an assembly was granted provisional approval. So it wasn't fully approved, but there was provisional approval, sort of like on the way, but not quite fully approved. There was an additional 3-year evaluation in the field before an assembly was granted full approval. After a while, it was determined that when an assembly continued to work properly for a year, then it would make it through the 3 years. So then eventually the standard was changed to a 1-year field evaluation. But the original standards did have just the provisional approval after 6 months and then required another 3 years in the field before an assembly was fully approved. The first edition of the manual was published in 1960, Manual of Cross-Connection Control Recommended Practice. These, again, included the standards, but then had more information about what practice should be taken in a cross-connection control program. These continued to develop through the years and then eventually moved on to what we have currently, which is the 10th edition of the Manual of Cross-Connection Control, which is it's over a 500-page document, which has all sorts of information about running a cross-connection control program, about hydraulics, about surveys and documents, letters need to be sent, all sorts of stuff about running a cross-connection control program, plus the standards for backflow preventers and the field test procedures that you find in chapters 10 and 9, respectively. So let's look at how these standards are developed. They are created by a manual review committee over several years. This edition of the manual took over 10 years to develop, with a manual review committee working during that period of time. And it takes a lot of work because you have different people from different areas coming together, taking in a lot of information from the public, a lot of input from various areas. So it does take a long time to put a manual together to make the changes necessary to publish a new edition. So it is a consensus standard, meaning that the entire committee really need to come to a consensus when we come up with issues. We come up with changes, we come up with new sections or whatever goes on in the manual. We do have to come up with a consensus as to what we're going to do. However, it is not an ANSI standard. An ANSI standard, American National Standard Institute, is there basically that has a very set way to have standards developed. And one of the things with that is they have a specific definition of how the committee needs to be made up. You have so many people that are different stakeholders. You have manufacturers and users, et cetera. With our manual review committee, the university felt that we really didn't want to have manufacturers writing the standard for the product they would be developing and selling. So that is something that sets us apart from there, that we don't allow manufacturers to be a voting member of the manual review committee. We do allow them to sit on the committee and to make comments, but they do not have a vote. So what we do have on the manual review committee is we have representatives of health agencies, water agencies, backflow prevention assembly testers, the BPMA, which is the Backflow Prevention Manufacturers Association. They have one member, so one member representing all the manufacturers. So we don't have just one manufacturer coming in and saying we want to do this or that. They basically need to come to a consensus among themselves, and then that one member will come in and voice their opinion as far as if the standard comes up with something that's just impossible to do, or the technology to manufacture the product that way is too difficult, then that would be something the Backflow Prevention Manufacturers Association would comment on, or they may want to come up with a new standard. They would comment on that and bring that to the committee. But they are non-voting members, so they cannot actually vote on issues for the manual, but they can comment on issues. And then we have USC Foundation staff, who are university staff on the committee. So this is our committee. This is how the committee is set up. And the committee gets together, discusses all the issues as we sort of work together to develop the new editions of the manual. So the approval program, which is outlined in detailed in chapter 10 of the manual, the USC Foundation approval program. This again is a long process. It is a 2-part process. We have the laboratory evaluation and the 1-year field evaluation. So like I said, the 6-month provisional approval, 3-year field evaluation was eliminated, way back with the first edition of the manual, I believe. But the current standard requires a laboratory evaluation and then a 1-year field evaluation. The 1-year field evaluation has 3 assemblies of each size and model in the field in different water systems, and and that is how our approval program works. It's not a rating system, so you will not find on our list of approved assemblies a rating for the assembly. We don't give it 5 stars, or 4 stars or 2 stars. It's either, it's got a star or it doesn't. It's either approved or it's not. Basically, it's either on the list or it's not. That's all there is to it. So I get calls regularly. I got a call this week just about, is this assembly going to be approved? It's either on the list or it's not. We don't know if it's going to be approved. And you'll see as we go through here why, because we don't know if it's going to be approved until the very last day of the field evaluation. That's when that determination is made. Our laboratory is ISO 17025 compliant, which is International Standards Organization for laboratories, just to make sure that there is a standard set there that, we're audited periodically to make sure that our equipment is working properly, that it's audited, that it's calibrated properly, that our people are trained properly, etc. So a couple things about our evaluation program is that all laboratory evaluation work is done by USC staff. We don't hire third-party labs to do anything. We don't hire third-party people to come in and do any testing. It's all done by USC staff at the USC Foundation laboratory. Manufacturers are not allowed to participate in the testing. They can observe the testing. They're allowed to be there and observe the testing when we're testing their products, but they're not allowed to actually participate in the testing. So that, again, is very important. We feel that it again, keeps the manufacturer separate from the approval of their product. This sort of outlines what happens when we go through the approval process, the submission of working drawings. We do a head loss curve. We take elastomer specs, spring specs, thermal loop, cycle test. I'm going to go through all these, so we'll look at this. So let's assume a manufacturer decides to get an assembly approved by USC. The first thing they do is they submit a lot of paperwork, but one of the first things they do is they submit the working drawings of the assembly. And we can look at the drawings and make some comments about the drawings. There are certain things we can't do. Most of the stuff we cannot do by looking at the drawings. We can't tell whether an assembly is going to have the right pressure loss across it, whether it's going to, the springs are going to close at a certain value or anything. The check valve is going to close at a certain value. We can't tell that really by looking at the drawings, but some things we can tell. We can tell the size of the test cocks. Large assemblies are required to have a 3/4 inch full flow test cock, fully ported test cock. We can look at the drawings and say, well, this isn't what's required. So there's some things we can look at the drawings, but that's the first thing we do, just sort of a preliminary look at the assembly to see if there are things we can spot right away that would be a problem, and they can get those taken care of before they actually submit a product to the Foundation lab for evaluation. So once this is done and everything looks fine, then they would submit a prototype usually to the USC Foundation for evaluation, and then we're going to start to look at different things. One thing is the head loss or the pressure loss across the assembly. And what we do here is we look at the pressure loss across the assembly at different flow rates. So we don't just have, hook up the assembly to the line and see how much pressure is lost at static with no flow through it. We check that at no flow, and then we increase the flow across the assembly gradually until we get up to the rated flow of the assembly. Then we slowly come back down, and we create a curve, which gives us an idea of how the pressure loss across the assembly changes at various flow rates. So as you can see on this curve, it goes up from 0 to 150 gallons per minute along the horizontal axis. At about 25 or 30 gallons a minute, you'll see on the vertical axis, the pressure loss across the assembly jumps up above 10 psi, 10 pounds per square inch. So that means if you have 100 pounds per square inch of pressure coming into the assembly, you have a little bit less than 90 pounds per square inch coming out of the assembly. So we've lost a lot of pressure. Now for double check valve assemblies, the maximum allowable pressure loss is 10 psi. So in this case, if this were double check, this would fail this test. So we would go back to the manufacturer, say, this assembly didn't pass, you need to do something to correct that, resubmit it, and then we would retest it. So we don't actually do we won't redesign the assembly for them. We will, let them know that it didn't pass and that corrections need to be made. For the reduced pressure principal assemblies, the pressure loss across the assembly varies with the size of the assembly. You can find that in Chapter 10 of the manual. Table 10.1 will describe exactly the pressure loss allowed at for various sizes of assemblies. So that is the pressure loss. Once this curve is generated, it gives you an idea. If you're going to install a backflow preventer, you see, you're expecting to have a flow rate of 100 gallons per minute. You can see here you'd be losing about 3.5 pounds per square inch of pressure across the assembly. So this curve can be very useful when you're designing a system or going to be using water for specific purposes. The elastomer specifications. Earlier editions of the manual required that the elastomer parts have certain hardnesses. So they would have a Shore hardness of a certain value. We don't do that now. Now the requirement is that the assembly has to have certain performance standards met. So we would try to foul a check valve by putting in a specific size fouling wire, and water would still not be able to leak across the check valve. So place a wire in the check valve, and the elastomer has to seal around that wire, no matter regardless of, even with that wire in there, still the elastomer has to be soft enough to seal around it. So we don't require it to be a certain hardness, but obviously it's got to be soft enough to seal across that wire. But again, if it's too soft, then it would leak. If there's no wire, water would just flow through it. So we don't have the elastomer requirement as far as the specific hardness, but there's still a standard for the elastomers. We do record this value, though, so we can go back later when we're maybe an assembly is coming up for renewal, or we've had complaints about an assembly. We can come back later and check the hardness of the elastomers and determine if the elastomer is the same elastomer that was originally approved with the assembly during its original evaluation. So we do record all this information so we can go back and determine if the assembly is still exactly the same as it was when we originally approved the assembly. The same thing with the spring specifications. Here we're determining the spring constant. We'll record the number of coils, active coils, coil diameter, wire diameter, as much information as we can about the spring. So again, years later, if we get a lot of complaints about an assembly, we can go out, pick up a new assembly off a shelf somewhere, bring it into our lab, pull it out, and we can look at the spring and determine, is this spring the spring that was originally approved with the assembly? Because we have all the data from the original spring, so we can determine if that's the actual same design as it was when we originally approved the assembly. A thermal loop. This is important because a lot of assemblies are rated for higher temperatures. Any assembly is rated at least 140 degrees Fahrenheit, so that's considered cold water. So an assembly has to be able to operate properly at 140 degrees Fahrenheit. In that case, the assembly would be put in the thermal loop at 140 degrees Fahrenheit. It's run for 100 hours. It's tested during that process, and then at the end, it's taken apart to make sure there's no deformation, no deterioration of parts, no damage. The assembly still operates properly. If the assembly is rated at a higher temperature, we've had some come in rated at 210 degrees Fahrenheit, almost boiling, then they go through the thermal loop at that temperature, again for 100 hours. It's tested during that process. It's tested at the end. It's disassembled to make sure there's no problems with the assembly. The assembly will continue to operate properly without any damage or anything. So the thermal loop is important. Whether it's considered a hot water assembly or not, it still has to be tested at least 140 degrees. So that is a part of the laboratory evaluation. Another thing we move on to is the cycle test. This was developed, I believe, with the 9th edition of the manual. And the concept of the cycle test was that we hoped it would help us spot things that might come up in the field. When an assembly's been in the field for a year and it runs through, water flowing through it, different cycles, opening, closing, opening, closing, opening, closing. If that would cause problems, we could hopefully find those problems doing a cycle test, correct those problems before we get out in the field. Because once it's out in the field, if it's been there for 9, 10 months, and then it develops the problem because of all the cycles it's run through, then changes have to be made. It goes back, starts the lab evaluation over, and starts the field evaluation over, and the approval process is pushed back another year at least. So the cycle test, the idea here was that it would help, and it did help. Before we had the cycle test, about 40% of assemblies that passed the lab did not make it through the field evaluation the first time through. After the cycle test, that dropped to about 30%. So it helped a little bit, but there is still a problem in that no matter what we do in the lab, we can't actually determine how an assembly is going to work in the field unless we actually put it out in the field and do the testing in the field. So again, that is very important. The cycle test is really important. This is a large cycle system for assemblies that are 2.5 inch and larger. We have a smaller cycle system that is for the smaller assemblies also. So failure to comply with any of the tests is cause for rejection or failure, and damage to the assembly is cause for failure. So this is very important because all all standards don't do this. USC is very specific in that if the assembly fails, obviously if it fails the test, it fails, but also if there's damage to the assembly, it fails. So that means you could, under some evaluations, you could damage the check valve, but as long as it holds, it does not fail the test. So for USC's evaluation, if it is damaged, then it does fail our test. So even if the check valve holds, if it's damaged, it would fail. So damage to the assembly is cause for failure, as well as failure to comply with the test would be cause for failure. Interesting thing that over 50% of the assemblies, this study was done between 2009 and 2012, and has continued in the process. We don't have the exact numbers since then because we haven't been tracking them as detailed, but it's still well within this guideline. Assemblies approved by other agencies, other listing agencies between 2009 and 2012. So they're already approved by another agency. They're on their list. Then they're submitted to USC for USC approval. Over half of those don't pass our laboratory evaluation. So that's very interesting in that it can pass someone else's laboratory evaluation, but does not pass the USC laboratory evaluation. So that is that's very critical. It doesn't pass our lab evaluation the first time through. Once changes are made, then it comes through and resubmits that, then it can pass. But assemblies that are listed by other agencies and then submitted to USC, more than half of those don't pass the USC lab test the first time through. Interesting stat. For our field evaluation, we require 12 months of trouble-free service, simultaneous trouble-free service for 3 assemblies of each size and model of assembly. They have to be in 3 different water systems. They first get installed, there's an initial test. We go out, test the assembly. We'll pull it apart, take measurements, make sure everything's the way it's supposed to be, that everything's the same as it was when it was in the laboratory. Then we do monthly field sites. We have a crew go out. Again, this is USC staff. We go out, we test the assemblies. If there's any problems, we determine what the problem is. If the problem is, you've got some sand on the line, that's not really an issue that we're too concerned with. We can, flush the water, let it continue to operate. If the problem is there's a material that's damaged or deteriorated, or there's something in the design that is a problem, then that becomes a problem and would stop the field evaluation. So we go through the monthly field evaluation. Then we do a final field test and a final inspection. So this is where we determine if the assembly is going to become approved. So this is why we cannot tell you if an assembly is going to be approved ahead of time. And again, that's a question I get. And again, as I mentioned, I got that question earlier. This actually was last week, I guess, Tuesday. So last week, someone called and said, "Oh, this assembly, we're told this is going to be approved. It's in the process. Is that true?" And one thing, I don't know. And another thing is we don't release that information, even if we do know, because of the fact that, someone in our staff knows, but I didn't know that. Because we don't know until we actually disassemble the assembly and determine whether or not the assembly is approved. So on that final field evaluation day, we disassemble the assembly, and there we could find all sorts of problems. And if at that point in time we find problems, then we know the assembly is not going to be approved. If we don't find problems, then it gets put on the list and it's approved, and there you have it. So that is how the final field inspection works, and that's why we can't really release information about an assembly until it's actually approved. There have been agencies that have allowed assemblies to be installed in their system because they heard that it was going to be approved at some point in time in the future, and they never became approved. So now you've got unapproved assemblies in the system, and it becomes a problem. So we never recommend anyone installing a backflow preventer that is not already approved by USC. If you require USC approval. If you don't require USC approval, then don't worry about it. Failure to pass the field test is cause for rejection, and damage to the assembly is cause for rejection. Again, the reason for failing to pass the field test would depend, assuming it's an assembly issue. Again, if you've got sand in the line and you can rinse that out, and now the check valve holds, that's not a problem with the assembly. That's a problem. You've got a problem in the water line, so that's not really an issue that would affect the approval of that particular product. But if it's clean and everything, and the check valve is holding low, then we have an issue with the assembly not working properly, or it's leaking. And again, damage to the assembly is also cause for rejection, as I mentioned. Not just does it have to pass the test, there can't be any damage. So even if it does pass the test but it's damaged, then that would also be cause for failure. Okay, about 30% of the assemblies that pass the USC lab evaluation do not pass the field evaluation the first time through. I mentioned that earlier. It used to be 40% after the cycle test kicked in. We dropped that down to about 30%. Another interesting fact is that about 70% of the assemblies that do fail in the field test fail in the last 3 months. So that is very important. Again, that sort of comes back to when we changed from the 6-month provisional and 3-year, the 6-month evaluation that gave provisional approval, and then the 3-year field test that gave the full approval. Once an assembly made it through a year, it would make it through the 3 years. But it had to make it through the years. Some people have suggested to us, why don't we go to a 6-month field evaluation, because it would be a faster process to get new products approved. And that's true, it would be faster. But you can see here that if that were the case, then 70% of the assemblies that now fail would pass. They wouldn't actually make it through a whole year, but they would have made it through the 6-month part. So it is important that we have the entire 1-year field evaluation, since most of the assemblies that do fail in the field fail in that last 3 months. Again, field evaluation is incredibly important. We cannot stress that enough. The only way you're going to know how an assembly is going to actually work in actual situation is to put it in that situation and test it in that situation to make sure that it is working properly. Okay, so the USC approval. Once an assembly actually becomes approved, it's given approval after it meets the laboratory, or pass the laboratory test and the field evaluation phase. It's put on the list of approved backflow prevention assemblies, approved for 3 years, and then renewal is required. And renewal varies depending a lot upon the feedback we get from people in the field. People like you, if you hear things, you have problems with a particular model and size of assembly, that is something we want to know. Now, if you have a particular problem with one assembly, like there's this one assembly down at this one place that always gives you trouble, that's one assembly, that's not necessarily an issue with the design of the assembly we want to look into. But we've had situations where someone says, the second check valve of this particular assembly continues, of this particular size and model of assembly, continues to be a problem throughout our system. Now, if that's the case, then we'll look into it. We would look into it. We'd want to find out from Water Health Agency with lots of data, does this seem to be a widespread problem? If it is a widespread problem, we'd grab an assembly again. We'd go to a warehouse somewhere, purchase an assembly, bring it down to our laboratory, look at it. Are the check valves the same? Are the elastomers the same? Are the springs the same? Run it through some tests and determine if anything's changed. If something has changed, then we would actually get to the point where we'd have to pull it off the approved list. Normally in that situation, what happens is we find out why something changed. We talk to the manufacturer, and if something changed by accident, and that has happened, things happen, then the manufacturer will put out a notice, and the manufacturer will provide parts to correct the issue and get the assembly back up to snuff. For example, an assembly several years ago, there was an assembly where the elastomers started to change. They weren't holding. They were softer than they should have been. The manufacturer changed vendors, and although the chemical analysis of the elastomer was exactly the same, the humidity where the elastomer was cured was different, and that caused the softness to change. And so the assembly wouldn't hold properly. So they made that correction. They made the correct discs available to customers, and so to maintain approval, USC approval, the customer would have to change out the discs, and we'll send out special notices when something like that happens. You get a notice from USC that specifically says, here's an issue, you need to contact the manufacturer, get these parts, change them out to maintain approval. And there are some cases where there may be a change that is just done and the manufacturer doesn't make corrections and the assembly would be pulled off the list of approved assemblies. So that could happen even if there's not complaints about it. I mean, if it's not up to the 3-year renewal time, if complaints come in, we do that. At the 3-year renewal time, we just start looking at assemblies and determine, is there anything that's been a problem, or are there any problems that we aren't aware of yet? Okay, so the assembly, once it's approved, gets put on the list of approved assemblies. This is we publish a paper copy of this every year. This is the internet. Currently, we're in the 2016 version. It's about It's over 500 pages. It's a big document. We send that out to members of the foundation if they request a copy of it. Otherwise, it's more up to date online. We have this available on our webpage and our web app, but it is available in paper format if needed. On the list, though, you will find a lot of information: the make of the assembly, the model, the size, the edition of the manual under which the assembly was approved. Now, this is interesting because we still have some assemblies on the list that are approved under the 5th edition of the manual. Until maybe 10 or 12 years ago, there was an assembly on the list that was approved under paper number 5. Do you remember that was the first publication in 1948? So the standards back in 1948 are a lot different than they are today under the 10th edition. So it's important for someone to know what edition the backflip preventer, what standard it meets. So you could say if it's approved by the 5th edition of the manual, that's a lot different than the 10th edition of the manual. So you'll find some water agencies or health agencies may require the assemblies to be approved from, whatever, 6th, 7th, 8th edition and later, whatever. The original approval date's listed on the list, along with the most recent renewal date. Also, you have the acceptable shutoff valves. When a shutoff valve needs to be replaced, every size and model of assembly has a list of shutoff valves that are acceptable with it that can be used to replace the shutoff valves to maintain approval. If you change it out with a different shutoff valve, it's not going to be approved anymore. Meters, same thing with meters for detector assemblies, the DCDAs, RPDAs, DCDA2, RPDA2s. Each size and model has a specific meter and acceptable meters that may be used to replace a meter if you need to replace a meter. Also, the orientation of the assembly, if the assembly is approved for horizontal orientation only, or vertical up orientation, or vertical down orientation, vertical up inlet, vertical up outlet, etc. All the orientations that an assembly is approved for are listed on the list with each size and model of assembly. Lead-free, less than or equal to 0.25% lead. We're going to talk a lot about lead-free issues today, but whether an assembly meets this requirement, it shows on the list for each assembly. And then if there are spare parts only. Spare parts only means the assembly is no longer being manufactured, but originally manufactured spare parts are still available. So it's still approved. You can get spare parts, you need to replace them, but they're not manufacturing the assembly itself anymore. So all this information you'll find on the USC list, and we'll talk about access to the list in a minute. USC Foundation membership, this was started back in 1967 originally by the Southern California Water Utilities Association. They collected funds from their members of water agencies in Southern California. They eventually gave a sum of money to the university as a gift to start the USC Foundation membership program, which then was in 1969 and that has maintained since that time. It's been the USC Foundation handles that. Members get email notifications every time the list is updated, every time there's a new special notice issued. So again, the special notice about product changing or something, parts need to be changed, etc. The list in its entirety is mailed out every year and at the member's request. Updates to the list are mailed quarterly, and they get a copy of the manual of cross-connection control each time it's published. Also, members get complimentary webinars. Several of you are getting this webinar today is complimentary because you're a member, and depending upon the size of your agency or the size of the membership, you get so many complimentary memberships or complimentary webinars a year. And the webinar on demands are also part of that. Crosstalk, our newsletter, phone consultation, discounts on everything, also available. So here you see the manual, left, the list of approved assemblies. Crosstalk's our newsletter, comes out quarterly, has information on specific things that are useful and informative to those involved in cross-connection control. And then again, the special notices that come out as needed regarding specific assemblies. Training events, we have training courses, tester courses. We started those back in 1971. Our first tester course became evident that there are backflow preventers out there. They need to be tested. People need to be trained to test them. We have those here at USC or in Los Angeles 4 times a year. Our next one here is at on the USC campus in January. The program specialist course, we started that in 1989. That is for someone who administers a cross-connection control program. Again, we do that 4 times a year. The next one's in January here. Live webinars, we do that several times a year. I think we have 6 or 8 of them scheduled for next year. 5, maybe 5, every couple months. The next one is in February. Again, that'll be a detailing of the USC Foundation approval program. The tester course covers background theory. The main thing about the tester course is how to test the backflow prevention assemblies. A lot of lab time, a lot of time working on the assemblies to actually do the field testing. Very good. It prepares you for certification for those certifying entities that use the 10th edition as their field testing procedures from the 10th edition of the manual. Lots of hands-on practice, lots of assemblies there to do the testing with. Program specialist course, again, for those administering a cross-connection control program, policies, procedures, rule regulations, site surveys is a big part of this course, doing reports, etc. Live webinars, these are great because they will give you the opportunity to just get updates. For the live webinars, you get continuing education units. Today is a 6-hour seminar. This is unusual in the sense that I think all of 2017's webinars are going to be 3-hour webinars. But that would give you 3 contact hours or 0.3 continuing education units. A lot of training tools are available. The manual, we'll just go through these actually. Manual cross-connection control. You guys hopefully all know what this is. If you don't, you need to get one. It has all the field test procedures, everything about cross-connection control you need to know. Laminated field test procedures for those involved in field testing. Field testing baffled winners instructional video. Nice thing is if you take our actual tester course during that week, you have access to this video, or parts of the video, live on your mobile device to help you go through the field test procedures. List of approved assemblies. Again, this is available hard copy. It's also available online at usclist.com. There's a web app there. You can look at it, look up assemblies there to see if they're approved, or look up types of assemblies to find out which ones are approved that meet your needs. Webinars on demand. Those are the webinars that we do here. They're recorded and then they become available at a later date. They're unavailable for another month or so, and then they're available for a series of 6 or 9 months, something like that. They're available for you to watch at your convenience for that period of time. Working Together for Safe Water, informational video, general. This is available on DVD. It's a general introduction to backflow. It's also available on our YouTube channel, I believe, already, almost already. Working Together for Safe Water, informational brochure, and then an informational brochure on household plumbing. PowerPoint presentation, helpful if you're, especially if you're a specialist making presentations to city councils or to homeowners association, help them understand what the basics of backflow are. PowerPoint presentation, you can add your own photographic slides specific to your city to be helpful. That's a great tool for those purposes. Some of the research projects we've been involved in, we've had several over the last years. An assessment of cross connections in North America, that was an AWARF study or Water Research Foundation study. Finding out what different water agencies, what their cross-connection control programs were like. You'd have to get that report from the Water Research Foundation since they sponsored that. Prevalence of cross-connections in household plumbing systems. That was sponsored by the EPA, so it's public information. You can download that report from our website, actually. Vulnerability project. That was another AWARF project, or Water Research Foundation, sorry. Water Research Foundation project, you would have to get that from them again. That looked at, how to determine if the water became contaminated in the system immediately, and we did a risk matrix situation for that part of the report. But again, you'd have to get that from the Water Research Foundation. We also have San Gabriel Valley Well Project. That's locally here in Southern California, where we basically measure the aquifer in the San Gabriel Valley, an area of Syria in Southern California. And that's been going on. We've probably been doing that for 30 years, where we measure and create 3D images of the aquifer underground here in Southern California. So that completes my introduction. Paul Schwartz will be coming on a little bit to start talking about repairs and lead-free issues. So we are going to take a 10-minute break. Be back right about 9 o'clock, and then Paul will start up with those issues then. So thank you.